Hi everybody, Patrick here from Engineering Shock Electronics, engineeringshock.com, and this is the bonus video for the Raspberry Pi without the Raspberry Pi. We're going to talk a little bit about the hardware. Not going to go crazy, but we're going to touch on everything. The schematic isn't fantastic. It's not laid out wonderfully, but again, it was never meant for anybody else but myself because the layout is the important part, and the layout is what this is the layout. In any case, what we got here is we got two methods of power supply. We got our USB here. You got our 5-volt jack here. It doesn't look like a 5-volt jack, but it's essentially a rectangle with positive. It says 12 volts, but 7.5 volts is optimal. Doesn't matter. It's just a reference point. So anywhere else in the unit where we see this 12-volt reference means it's connected here. And this is ground, DC ground. This is an AM1117 5-volt regulator. So when power is plugged in here, it regulates down to 5-volt here. We got a smoothing cap and a decoupling cap. And then we've got the regulated output, 5 volts, which is right here. There's a 3-pin jumper right here, which allows for us to choose between USB and the external power supply jack. So if we select EXT, we'll be selecting this power supply, and you're using an external 7.5 volt power supply to insert power. Otherwise, you've got the middle pin and the bottom pin here connected in. That means that you've got USB power connected. VCC is our reference point for 5 volts. So it's either going to come from here or from here. Now the USB also connects to the CH340G. Ignore this in the middle. It's blacked out. I'm just stealing the package. What I should have done is I should have created a package from scratch, but I was feeling lazy that day, and that was about 3 years ago, and this still works. Whenever I use a CH340G, I just copy it. So these are the pin numbers. 2, 3, 4, 1, 15, 14, 13, 16, and we don't use any of these. And so the data plus and the data minus pins go from the USB to pin 6 data minus and pin 5 data plus. And this is our USB bridge chip. The TTL compatible outputs, TX and RX, are here, and they connect to TXD and RXD pins on the microcontroller. And we've got a decoupling capacitor on the power lines here, between VCC and ground, between here and ground. These two capacitors are 22 picofarad, and they're in parallel with the 12 megahertz oscillator, which connects to XTAL1 and XTAL2 on pins 7 and 8. It needs this to operate, and these capacitors help the crystal to function properly. There's a capacitor between ground and pin 4, and there's actually regulated 3.3 volts on here, but it's a very weak 3.3 volts, so we don't use it. Just add that capacitor if you're going to. Pin 1 is connected to ground. Pin A16 is connected to VCC, and 5 volts. And this, you see this capacitor here? Capacitors will block DC voltage, but they will allow for AC to pass. So what this does, this is actually connected to the microcontroller reset line, which is pulled up to 5 volts via a 1 k ohm or 10 k ohm resistor. So what this does is when this line's activated, right before we start a programming sequence on the TXD and RXD lines, is it actually pulls that 5 volts on, or that current limited 5 volts pulled up to 5 volts on the reset line and pulls it low. So it's just an instantaneous pop where it resets the microcontroller and puts it into mode where it can start programming. So hopefully that makes a little bit of sense. I'll show you just in a second. So if you look at the reference point, it goes to RST. So again, think about this as nothing going on here until this line is pulled low, at which point it'll cause a dip on the reset line through this capacitor. So now I'll look at the microcontroller. This is the Atmega 328P, and we're actually using a PBAU, but it's still a variant of your standard Arduino. We've got a 16 megahertz crystal oscillator on pin 7 and 8, XTAL1 and XTAL2, with another set of 22 picofarad capacitors to ground, which help the 16 megahertz oscillator work. That clocks the chip, just like the 12 megahertz on the CH340G. AREF, this is our analog reference point. We're not doing anything with it, so we're just going to decouple it to ground. AREF you can set analog reference voltage, but we're just going to be using VCC, which is 5 volts. If we did add 2.5 volts to this line as opposed to setting it to ground, then our reference point, and there's a change in software you need to do as well, but you can actually set using this pin, you can just set a reference point for your ADC to a different voltage than 5 volts. Look it up if you're interested. It's easy. So we've got a bunch of we got pin 18, 4, and 2 set to 5 volts VCC. As you can see, we've got RST reset connected to VCC through a 10 k ohm resistor. So the capacitor on the CH4Z is connected here, and so when it receives data from the PC, it pulls this line low, setting the Atmega chip into a programming mode, and then the TXD and RXD pins are used for programming through the CH340G. So the CH340G is a USB bridge. It takes USB, converts it to a TTL compatible signal. We've got our analog to digital pins. We use A0 to A5. These are our digital pins. 0, 1, we're not using it for anything other than programming, but GPIO 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 10. This is 11, 12, and 13, but we're not really using those for anything other than SPI. SPI is a communications protocol, and we use that for programming the bootloader. We got MOSI, which is master out, slave in, MISO for master in, slave out, and SPI clock. We got pins 21, 3, and 2 connected to ground. Now this is our boot loader header. And the only reason we use this is two things. We can program we can program any Arduino program using ground, reset, TXD and RXD and 5 volts. We can program it externally using those pins if we want, but mainly I have this here for programming the bootloader of the chip, which is done before you get it. So when you program a bootloader, if you want to learn how to do that, every blank Atmega chip that's used for Arduino needs a bootloader. And in order to install the bootloader, there's a whole other video. It's easy to find instructions on how to do it online, but you need an external Arduino, the reset line, the S clock line, MISO, VCC, ground, and MOSI. TXD and RXD are only used for programming. And we got some decoupling capacitors here between the power lines and the ground, between these pins and these pins. This is our buzzer. It's a hideous schematic, I apologize, but we got the positive of our buzzer connected to 5 volts and our negative is connected to a transistor switch connected to ground. This 10 k ohm or 100 k ohm resistor pulls this line low. It's not even that necessary, but it pulls it low just in case this line becomes floating or starts to float. And even if it is floating, it still won't activate, but this is just kind of just in case. This is a 1 k ohm resistor. And when I say K, I mean 1,000, so 1,000. This is 100,000. And that's connected to the buzz line. So if we look over here, when we connect our analog pins and GPIO pins to the sensors, we use jumpers. So if we want to use the buzzer, we connect A5 to buzz with a jumper. And yeah, this is our light dependent resistor right here. It's connected to a 10 k ohm to VCC to 5 volts. So what happens is this is a variable resistor. The resistor is variable based on how much light is touching it. It's much higher resistance when there's low light and very low resistance when there's high light. And that changes the voltage on here because this is fixed. If we had a 10 k ohm resistor here, a 10 k ohm resistor here, and VCC was our reference, then we'd see 2.5 volts here fixed. But because this is variable, we'll see a variable voltage depending on how much light there is. And we use our analog to digital converter to read that voltage. This is our motion sensor. Now there's a lot going. This is a PIR motion sensor. It's connected right down here. This is all your PIR sensor stuff right in here. This is our light sensor, our microphone, our temperature sensor down here, our infrared sensor here. But what we got here is our power supply. So this is the power supply pin to the motion sensor. It's a D203S with a Fresnel cap. So as you can see, we got lots of smoothing and filtration going on. And we've also, so what we got is 5 volts, current limited through 3 10k ohm resistors. And we got these big bulky 100 microfarad capacitors here with decoupling capacitors here. Decoupling, so decoupling capacitors typically 100 nano or 0.1 micro, 0.1 U. So we've got, for every resistor we've got a decoupling capacitor to ground and a smoothing capacitor to ground. That makes sure that this is a nice, relatively noise-free power supply circuit. We got this pin connected to ground. So now this is our power supply right here, connected to here. Now this is our signal output. So there's a bunch of filtration going on here. They're using RC filters and an active RC filter. And what this is this we get a very tiny signal here when motion is detected. When this detects an infrared spectrum coming off a human or animal body, we'll get see an extraordinarily tiny signal here, very tiny. And so what we need to do is clean it up with some RC filter. We need to use an active meaning powered RC filter. We're using an op amp. I'm using LM724 because it has 4 op amps on the chip and they're very cheap. And so there's a bunch of active filtration going on using RC filters. And so here we'll see a usable signal, but we want to boost it up even more. So there's a bunch of low pass filters in here because high pass we want to filter out high frequency, and we want to allow for low frequency to pass. So the actual, if you look at the waveform of the output of the motion sensor, it's relatively noise free, but you can see the huge low frequency swing when it notices motion. So what we got here is we've got a resistor divider here, so 150 k ohms here, 10 k or 100 k ohms here. So we're going to see about 2 volts here, and what this is going to do is it's going to create a bias. So by default, the output we'll see when it's resting, we'll see about 2 volts. And when we get a boosted signal through here to the negative input, what will happen is we will see a change to that other, where the voltage exceeds 2 volts or goes to below 2 volts. But resting, we'll see about 2 volts because of this bias. And we've got some nice decoupling and some smoothing capacitors in here as well. And this is the output. We didn't need to have a voltage divider here, but I put one in anyway. And so the reason for this is because I recycled this design from something else. And I think the other thing was 3.3 volt compatible, whereas this is 5. So this wasn't necessary. I could have just placed the motion sensor connection here. But this is the output of the microcontroller right here. This reference point right here is the reference voltage for the motion sensor, which is right. Come on. PIR, sorry, right here. Connects to pin A1 when you add a jumper here. Okay. We got a relay. The relay pin connects between here and this base of this transistor. We got 100 k ohm pull down, not necessary, but whatever. This is the coil of the relay. It's literally just a coil of wire in the relay. When you energize it, it turns these relay switches on. So when the relay is off, the common pin labeled P is connected to the NC pin, normally closed pin, and when the relay is turned on, the common pin disconnects from the normally open pin and connects to the normally open pin. And when the relay is turned off, it disconnects from the normally open pin and connects back to its default state with the normally closed pin. And this is just a terminal block right here. So CO connects to NC when the relay's off, it disconnects from the NC and connects to NO when the relay's on. What we got here is, so when a 5 volts is connected here, it activates this relay, this transistor switch, so power flows through the coil of wire to ground because this is active, and when this is removed, no current will pass to this transistor, so this will be turned off. This is called a shunt diode, and what that does is when the magnetic field collapses, when the power for the relay is removed, this coil of wire, there's this essentially a little bit of just a voltage spike, because when the magnetic field collapses, it creates that voltage spike. So this is called a shunt resistor, and it helps to alleviate that. And an LED here, 1.5 k ohm resistor, current limiting resistor to our LED. Our LED is located here, and we can control it with GPIO pin 13, which is also S-clock, by adding a jumper here. Microphone. Okay, so there's a little bit of an amplifier here. I'm not going to get into this too much, but realistically, all you need to get it to isolate a little bit of audio is connect VCC to a 10 k ohm resistor to the positive pin of the microphone, negative to ground, and then we can use this well, in this case it's a coupling capacitor, to send over a audio signal. So we'll have a DC bias here. We get rid of it. We just have the AC signal here. But what this is just a little amplifier circuit. So the signal gets kind of amplified a little bit right here. And without this pull down resistor, we will have this 100K pull down resistor. We'll see a mess here. So very necessary. And that is to the mic circuit, which is here. So if you connect a jumper, the audio, you'll get audio signal to A2, analog pin 2. This is our temperature sensor, and this is an MCP 9700. Connect 5 volts to the VCC, ground to ground. We've got a 0.1 microfarad electrolytic capacitor across VCC and ground to eliminate a little bit of noise. I think I should have added another capacitor actually to that. I think I should have added a 1 microfarad electrolytic capacitor, because I do find that this is a bit noisy and I don't like it. But either way, you can still get results from it. It's just not the best. So I think if I could go back, I would have added another capacitor in parallel with this, probably a 1 microfarad. Anyway, this is our temp output. We got a little decoupling capacitor here, and temp right here. So the A0 line can read the temperature voltage. The Ext. This is just an external signal option. It's on the side here. So this is if you want to connect an external signal, you can do it here, and here's a ground connection, and that connects to here, EXT. A4, we don't use it in any of our projects, but it's there if you want to use it. This is our, what is this? Yeah, so this is essentially this. It is our signal connection board. This is an external signal line, which with TXT, RXT, MISO, 3 ground pins and 2 VCC pins, and it's located over here in case you want to use any of that. That's up to you. I don't use it in any of our projects. But here's the LCD. If you want to learn more about the LCD, just Google 1602 LCD, and basically there's explanations here. I don't really want to go into this too much. Pin 1 is connected to ground. Pin 2 is connected to 5 volts. That's the power supply line. These 2 pins are A and K, are the power supply pins for the backlight. As you can see right here, we have it also A connected to 10 volts through a 100 ohm resistor to current limit it, and the negative is connected to a transistor, and this is our LCD enable line. We're using MOSI for it, and when that's turned on, then power will flow through VCC, through the current limiting resistor, through the backlight LED, and ground, completing the circuit. When this is turned off, the backlight will be turned off. These are the 4 data lines right here. GPIO pins 10, 6, 5, 5, and 4. And then there's read, write, and enable. These pins here. This pin 3, is the contrast pin, and that shows that determines how bright the characters in the LCD are. And I've got it set to, I think I've got this one set to 3.3 k ohms. Anyway, when you want to activate the LCD, you want to make sure there's jumpers across all of these. Have I covered everything? I feel like I have, but here we go. This is one thing I was missing. So this looks weird. This is a weird layout. I created this package myself. and this is the infrared sensor. So the IR sensor has 4 pins, 2 ground pins, a power supply pin, and our output line. This is our output reference line. So that's actually IR is connected over here to GPIO pin 7. Sorry, when you add a jumper here. So what this is we've got 2 capacitors here. I think it's a 100 microfarad and a decoupling 100 nano between VCC and ground. We current limit this VCC line using a 100 ohm resistor, and what happens is the output is also pulled to 5 volts through this 10k ohm resistor, and so when an infrared signal is received, it drives the signal line low. So basically this line will sit at 5 volts, and when it receives an IR signal, it'll be pulled low, and you'll see a signal go like this, and once the signal is received, it goes back to 5 volts and just stays there. So this is pulled high. This is current limiting to the chip, just in case the output shorts. So we got, again, current limiting to the chip. These are the 2 grounds. And here's the bad boy right here. So I think that's it. There's our buzzer, our power supply regulator, CH340G with 12 megahertz oscillator, our FTDI bootloader header, Atmega 328P, 328 PBAU, our relay, terminal block, drive circuitry for the relay, LCD drive circuitry. We got our buzzer here, 16 megahertz crystal for the chip, motion sensor circuitry, temp sensor, light sensor, microphone, IR sensor, signal selection, external selection, and this is how our LCD connects to the board right here. Thanks so much for your pledge, guys. I hope this video was informative, and I hope you enjoyed it. Take care.